Recall our diamond data set that we were looking at where our x was caret and our y was price. We fit a model we fit the least squares equation minimizing y minus beta naught plus beta 1x. We minimize that least squares equation. We discussed how there was at least two ways to think about this. One was to find this best line that fits the data, minimizing the sum of the squared vertical distances between the data points and the line. The second was to think about y as a point in n-dimensional space, which in this case we're just going to visualize it with R3. Y is a point in n-dimensional space, and the plane beta naught jn plus beta 1x was the two-dimensional plane cutting through y-dimensional, the n-dimensional space, and the beta hat was the specific combination of points jn and x that led to the point right here, the projection of y onto that plane, which we'll call y hat. So y hat is equal to beta naught hat plus beta 1 hat x. So in this case, it's this whole vector. And then if we're visualizing it in this left-hand case, the y hat, each component is just the projections, or is not the projections, is the straight line distance, minimum distance points onto this line right here. So if this point is this combination is x5, y5, then this point right here is y hat sub 5. And y hat is the vector of y hats. So y hat is defined as beta, if I'm being technically correct, which is the best kind of correct, it should be y naught, beta naught times jn plus beta 1 times x. Okay, so y hat are the fitted values. It is the projection of the data point y, the n-dimensional data point y, onto the two-dimensional space defined by x and the constant vector. And another vector of interest is e, the residual, which is y minus y hat. So every element of E, for example, is this distance. So E5 would be the distance between Y5 and Y hat 5. E, visualized in this left-hand picture, is the vector right here, is the vector that is orthogonal to the plane that points up to the data point Y. So it's probably best visualized if we drew it from the origin. It's over there. So E, it makes sense, by the way, and this will come up later on, that the vector E is orthogonal to every point in this purple plane that I've drawn here. Okay, so E are called E, the vector of differences between Y and Y hat, is the vector of so-called residuals. If you can think about our least squares criteria is actually, well, we could think about it as minimizing Y minus Y hat squared, where y hat takes on this specific form with the beta naught hat and finding the best beta naught hat and beta 1 hat. Or we can also think about our least squares equation as minimizing the sum of the squared residuals. Okay, so these are two important concepts: the fitted values y hat and the residuals e. So let's go through a computing example where we just compute each of these quantities. We'll revisit these very frequently throughout the class as they're essential to regression. Oh, one last comment on y hat. If we wanted to predict a price for a given caret value, that would be y hat. And notice we don't have to only predict at where we observed x values. If we wanted, for example, to predict right here, we could plug in an x value that we didn't observe and get a predicted y value out. Now that wouldn't be a y hat value because y hat is specifically the vector of predicted values at the observed x's, but this illustrates how we would get predictions at x's we didn't observe, just plugging straight into the line that we fit.